This is the second problem from Exam 1 given in Thermodynamics 1 Spring 2023. We're looking at a Joule-Thomson expansion, which is often used to liquefy gases. It's often used, for example, to create liquid nitrogen. And so we have gas at a high initial pressure, P1, and temperature T1, and it's flowed through a throttling valve that reduces the pressure to P2. The gas flows rapidly through the valve, so we can assume that no heat is transferred from the gas or to or from the gas. During the process, we can also neglect any changes in kinetic or potential energy. Assuming the information above, what is the enthalpy change of the fluid going through the valve, delta H, right? So let's draw a picture. So if I usually draw throttle valves like this, we have state 1 outputting state 2, and P1 and T1, P2, T2, and note that P2 is less than P1. And we need to determine delta H, that's what we're interested in. And so let's take a look at the energy balance. We're given equation sheets for this exam. The energy balance on an open system can be found here. So I don't know if this is explicitly stated in the problem, but it's not stated that it's not at steady state. So I would assume it's a steady state process, which would make it 0. We assume there's no change in kinetic energy, which means that this term, delta U squared, is 0, and the delta ZG is 0 because there's no change in potential energy. So we have a delta H times, oops, I didn't mean to cross, delta H times M is going to equal Q times W. Notice the negative sign, so I can move this term to the other side. So let's come back. So delta H is going to equal Q plus W. Now, it is also, sorry, I just want to repeat, no change in kinetic energy, no change in potential energy. And notice here that we say no heat transfer, so this is also 0. The problem does not explicitly state anything about W, but we expected students to know that this is just a valve. And so if it's just a valve, it doesn't have an impeller or anything that resembles a pump or a turbine. Therefore, it actually isn't capable of extracting work. And so the delta H is actually 0. So in other words, H2 equals H1. And I believe that is the answer to the question. The question does ask us to list assumptions. So I would actually say no mechanical work, for a valve. The other assumptions are given to us, so no heat transfer, neglect changes in potential energy. I would underline those, but those are assumptions that are given to us. I don't think we need to state any of them. And I think that answers the question. So now the second part, consider the Joule-Thomson expansion of a gas starting from, okay, we're given P1 and P2, or sorry, P1 and T1, and then we're also given P2. What is the final temperature? Is it a gas, is it a liquid, or a mixture? Okay, we have the following data. So if we're given 200 bar, let's say pressure 200 bar, hopefully it's one of these lines, so one of the first two lines. T1 is 300, so this is state 1. And so we know the enthalpy of state 1 And notice that there is only one other enthalpy on this list that matches the enthalpy of state 1. Remember, this is a constant enthalpy process. So we're given the output pressure, which is P2, which is 1 bar. Oh, good. So this is state 2. And what are we asked to do? Okay, what is the final temperature? So that means T2 equals 270 Kelvin, and the phase is a gas. That's here. Okay, that looks right. And part C, Dr. Gartner spilled coffee on the above data table. Oops, oh, that must be this. That's a rather small amount of coffee. We don't know the enthalpy of saturated liquid nitrogen at T equals 77, P equals 1 bar. Okay, so under these conditions, we don't know the enthalpy. I don't yet see why we would want it, but okay, calculate this value. Okay, so now we know why we want it because the question's asking it. And using the data below, okay, and the properties of nitrogen. Remember these unit conversions. Okay, so what we've got here is a series of temperatures, and they surround the temperature of interest, 77.2. And we have the saturation pressure, the volume of the liquid, and the volume of the gas. Okay, what we want is the enthalpy of the saturated liquid. So we want HL. Okay, and it should be related to the pressure and the molar volumes. So I think I know what we want. So under latent heat, because it's related to phase transitions, we have the Clapeyron equation. So I don't have to, I'm just gonna write it down and then copy it. Delta H equals T delta V dP sat dt. So that's the Clapeyron equation. And I can come back here and see if I can use it. Okay, so we know that, so delta V is going to be the difference between the vapor and the liquid molar volumes. Now we can get temperature, we know the temperature, so we need to evaluate how pressure depends on temperature to get this dP dt. I should also point out that delta H given here is going to be the H of the vapor minus H of the liquid. And so if we want H of the liquid, that means H of the liquid is going to be H of the vapor minus delta H. Okay, and oh, how nice. We're given H of the vapor. H of the vapor is 230 in this table. So this is equal to 230. Check the units. This is kilojoule per kilogram. And so we ought to be able to compute delta H. So delta H is going to equal 77.2 Kelvin. That was the temperature we wanted, right? Sorry. 77.2 is correct. Times delta V. Delta V is going to be at 77.2. Oh, here we go. This is going to be 0.22 meters cubed per kilogram minus 0.00124. And now we need to evaluate dp sat dt. I'm going to give myself a little more room here. And so that is going to involve looking at a delta P over delta T from this table. And so here are the pressures, here are the temperatures. Since we have something above and below, let's go ahead and use a centered finite difference formula. So this is, we're going to approximate dp dt as being now, by the way, we're probably going to have to do a unit conversion here because our other units are in meters cubed Kelvin. So I think we're going to have to convert from bar to Pascal. Oh, okay, it's just a 10, here it is, it's given here. Okay, so we're gonna need to do a delta P, so I'm gonna say 1.12 minus 0.88, so that's bar, and then times 10 to the 5th pascals per bar. And the delta T is going to be, 78.2 minus 76.2 Kelvin. And let's see, the Kelvins cancel, and hopefully, I believe meters cubed is the standard unit, or kilograms meters cubed is the standard unit within pressure. And so you can calculate this number, delta H equals 202.7 kilojoules per kilogram. And then you can say HL equals delta H of the vapor minus delta H of the phase transition. Oops, sorry, I shouldn't say delta H of the vapor. I should just H vapor, which is going to equal 230 minus 202.7 kilojoules per kilogram. And that comes out to 27.3 kilojoules per kilogram. Okay, is that what it was asking for? Okay, yes, we want this enthalpy. Okay. Okay, so I think that's right. So now consider Joule-Thomson expansion, 200 bar, T equals 133 to 1 bar. Hopefully we have the data for that. Yes, 133 is here in the table, and so is 200 bar. And this process results in a mixture of saturated liquid and vapor at T equals 77.2. What is the mass fraction? And the hint says specific enthalpy of a saturated vapor, or liquid vapor mixture, sorry, is the mass fraction weighted average of the two enthalpies. Okay, so if we know that H input is this 133, which comes out to 150 there, that means that the H output, right, let's draw this as, we'll call this H in, I'll call it H1. it's not the same as earlier H1s. And this is H2, but we know that we have this property, H2 equals H1, which from the table is going to equal 150 kilojoules per kilogram. So this is 150 kilojoules per kilogram, and this is going to equal, so I'm going to call this X times H liquid at 77.2 Kelvin plus 1 minus X times H vapor, 77.2 Kelvin. Okay, so we computed this to be 27.3. We computed this to be 230. So we should just solve for X. And, well, when you do that, that will come out to, so let's say 150 equals 27.3x plus 230 minus 230x. And so you solve for x. I'll let you do the algebra. You're going to get x equals 0.395. This is the mole fraction of liquid. The mole fraction of vapor is 1 minus that. Sorry, not mole fraction, mass fraction. Liquid versus vapor. So the 1 minus x vapor, is going to be 0.605, assuming I can do math correctly. Okay, I think we're done with this.